Welcome! We present Object Pop-up, a method to infer 3D objects from human interactions. Interacting with objects is part of our daily life. Human-object interaction is led by geometry, functionality, and features. But what if the object is not present? In this video, Jerry Lewis interacts with several objects that are not present in the scene, such as a piano, a door, a teacup, and a banana. We can easily visualize all these objects. They naturally pop up in our minds. This observation inspired our curiosity. Can we understand the object from human interactions only? How much information is stored in the human body? Which parts of the human body are relevant to infer the object? At first sight, these problems sound highly under constraint. Nevertheless, exciting properties of our perception allows us to visualize these objects. We found inspiration in behavioral studies, particularly in Gestalt psychology. They state that the single parts might not be enough to understand the whole. But when many single parts come together, we also perceive their relationship, which provides much more information. Similarly, a single hand might fit several different objects. However, when all the body parts come together, their relationship constructs a powerful representation in our mind. This allows us to visualize post objects even without their presence. The study of human-object interaction in a 3D environment is of great interest to the community. Recent methods can generate realistic and physically plausible grasps, synthesize human motion, and generate interactions that satisfy user requirements. These studies tend to model the human-object interaction starting from the object. Instead, in this work, we invert the perspective. Starting from a human, our goal is to recover the involved object. Concretely, given the input unordered 3D point cloud of a human, our goal is to predict the pose of the object involved in the interaction. We will explore both the case with a given and an unknown object class. While solving the problem, we faced several challenges that motivate our design choices. We aim to support as many input data sources as possible. Therefore, we choose to work with unordered point clouds, thus making the problem harder but expanding the applicability. Moreover, interactions often happen in localized regions. This requires additional local context to enrich the global features with interaction-specific ones. To represent predicted object position in 3D space, we decide to use a representation richer than 6D pose, which is per point offsets of object key points. For offset prediction, we sample the same number of points on each object's surface once and reuse it later. This allows us to support arbitrary object mesh configurations. These challenges directly influence the design of our architecture. A input point cloud is used to extract global features and infer the object center. After that, the object template and corresponding set of key points are selected. Then, the center is used to obtain a local neighborhood and extract features from it. All the extracted features are used to predict offsets for the object key points. Finally, during the post-processing step, the object template is fitted into the predicted key points location. Next, we present results of our object pop-up method. Here is a result on a sample from the grep dataset. The Behave dataset was recorded with Kinect sensors. We can directly use the provided raw point clouds for the evaluation of our method. Our method generalizes to raw point clouds from the Behave dataset. To further evaluate our method, we record data with variable IMUs. Here we present the result obtained from IMU data. To get more insights into the problem, we study the saliency of the input points to find which body parts influences the prediction. In red, we highlight the parts of the point cloud that has the highest influence on the final prediction. As expected, the interaction region is always essential to infer object position. Feet also play an important role. They provide insights into the pose and orientation of the human, coupled with the head region. Can we solve an even harder and more general problem, predicting the object class given the input point cloud? Yes, but the task is ambiguous by nature. Most of the poses are too common and can fit multiple objects. Thank you for watching. In the following part, we present more results of our object pop-up method.